everybody's back from break. So before break, we were talking about million instructions per second as one of the measures of computer performance. We have done a simple example to calculate million instructions per second for two computers and found out which one has higher million instructions per second. And we found out which computer is very fast between these two computers, computer A and computer B. To find that, we only focus on the CPU time, not on the number of million instructions per second. So the second concept that we're going to learn is the CPU time. The CPU time can be improved by reducing the number of clock cycles or by increasing the clock rate. So we have the CPU time. The CPU time equals to CPU time The CPU time is given by the following expression. CPU clock cycle, CPU time, equals to CPU clock cycles times clock cycle time. Times clock cycle time. This is the one expression to know the CPU time. All is also equals to the CPU clock cycles divided by the CPU clock rate, as the clock rate is the inverse of the CPU clock time. So this is what we have. The CPU time equals CPU clock cycles times clock cycle time, or CPU time equals to CPU clock cycles divided by the CPU clock rate. This can be, the CPU time can be improved. I mean, the performance of the computer can be improved. When you consider the CPU time, the performance of the computer can be improved by reducing the number of CPU clock cycles or by increasing the CPU clock rate. So considering the computer performance, here CPU time is very important because we always want our computer task to be done in less time. So this can be improved, the computer performance can be improved, one, by decreasing the CPU clock cycle so that our task can be done in less CPU clock cycles, or by increasing the CPU clock rate. To understand this, we have a computer A, which has a clock rate of 2 gigahertz, and it takes only 10 seconds of the CPU time to run a program. And you wanted to design another computer B, which should run the same program in 6 seconds. However, using a fast clock increases the number of clock cycles. And we have seen that increasing the number of clock cycles by a factor of 1.2. So which clock rate must be computer B? You have also 3 minutes to complete this exercise. 3 minutes to complete this exercise. You needed to tell me what is the clock rate of computer B. 3 minutes. Finish? Done? Hello, everybody, please do this exercise. I say to do it. You don't have a notebook? What is the clock rate for computer B? Huh? 4 gigahertz. How did you found it? Now, we know that computer A has a clock rate of 2 gigahertz, and it takes 10 seconds of CPU time to run a program. And we want a computer B, which can run the same program, but in only 60 seconds. But we know that a fast clock increases the number of clock cycles needed by a factor of 1.2. So we wanted to calculate the clock rate for computer B, which equals CPU clock cycle computer B divided by the CPU time for computer B. But we don't know the CPU clock cycle for computer B. We only know that because we wanted to increase the clock rate, it has to increase the CPU clock cycle by a factor of 1.2. That means the CPU clock cycle of computer B is 1.2 times the CPU clock cycle computer A. CPU time computer B. So we wanted to find out what is the CPU time, the CPU clock cycles for computer A, which equals the CPU time for computer A times the clock rate for computer A. That is, the CPU time for computer A is, CPU time is 10 seconds, right? And the clock rate for computer A is 2 gigahertz. That is 2 to the power of 9. Then the number of CPU clock cycle is this much for computer A. So since we have the CPU clock cycle for computer A, it is much easier for us to find the clock rate for computer B. We have 1.2 times the CPU clock cycle for computer A, that is 20 times 10 to the power of 9. And we have the CPU time for computer B, which is 6 seconds. And this is 24. 24 divided by 6, that is 4. 4 to the 10 times 10 to the power of 9, that is 4 gigahertz. You're right. Questions? Clear for everybody on how we found the clock rate for computer B? So if you want to increase the clock rate, it will also have to increase the number of clock cycles needed by a factor of 1.2. That means the CPU clock cycle for computer B equals 1.2 times CPU clock cycle for computer A. We have the solution. We have the clock rate for computer B, which equals the CPU clock cycle computer B divided by the CPU time for computer B. And we need to calculate the clock cycles for computer A equals the CPU time times clock rate A. So we just found the number of clock cycle for computer A. That's much easier for us to find out the clock rate for computer A, because it is equals 1.2 times clock cycles for computer A divided by the CPU time for computer B. Now, the next computer concept that we're going to learn is about instruction count and the cycle per instruction. We have instruction count for a program, and this is determined by a program itself, and instruction set architecture and the compiler. We have average cycle per instruction. This is also determined by the CPU hardware itself, and if we have a different instruction, we need also to have different cycle per instruction. We can calculate the average CPI, average cycle per instruction, which is affected by instruction mix. So clock cycles we have the clock cycles equals instruction count, clock cycles equals instruction count, let's say IC, times cycle per instruction, CPIs. Cycle per instructions. CPI or we have the CPU time equals to instruction count, IC, times CPI times clock cycle time. Then the CPU time equals instruction count, IC, times CPI divided by the clock rate. Here is instruction count and the CPI. These are also important concepts to evaluate computer performance. We have a simple example here. We have two computers, computer A and the computer B. The clock cycle time, one is 250 picosecond, another one is 500 picosecond. We have the CPIs, one is 2.0 for computer A, and another one B is 1.2. They all have the same instruction set architecture. So which computer is fast? Hello? Which computer is fast and how much? We have the expression to calculate the CPU time. I want you to tell me which computer is fast and how much. 2 minutes. Minutes to complete this task. How much? How much is fast? How much time is fast? 2 questions. 100. Okay, I want you to tell me how many times our computer A is faster than B. 1.2. How did you found it? You right? How did you found it? Huh? Tell me. We have the CPU time here. CPU time equals to instruction count times CPI times clock cycle time. Now, CPU time for computer A, tell me, equals instruction count times CPI. The CPI for computer A is 2.0 times clock cycle time for computer A is 250 picosecond. Then we have the CPU time for computer A, IC times 500 picosecond. Now we need to calculate the CPU time for computer B equals IC times 1.2 as CPI for computer B times the clock cycle time for computer B, that is 500 picosecond. Then we have IC times 600 picosecond. Now we need to find out which computer is fast and how much. We get we use the relative performance CPU time computer B divided by the CPU time computer A. Then we have IC times 600 picosecond divided by IC times 500 picosecond. And since these two computers, they have the same instruction set architecture, that means they have the same instruction count, we have 1.2. So our computer A is 1.2 times faster as computer B. Clear? Clear? So this is the solution. We have our computer A, CPU time, computer B, CPU time, and we need to calculate the relative performance by taking the CPU time for computer B divided by the CPU time for computer A. GPI, different instruction classes take different number of cycles. So we need to calculate the clock cycles equals the summation of CPI's time instruction count. So here we have the summation 1I from I equals to 1 to n, when n is the different number of instruction classes. We have CPI, since each instruction type has its own CPI times instruction count, then we get what we call the clock cycles. CPI equals to clock cycles divided by instruction count equals the summation of CPI's time instruction count I divided by instruction count. This is what we call relative frequency. So we have also the summation from I equals to 1 to n, and n is the number of different types, instruction classes that we have. We have different classes of instructions. Different classes of instructions. And the clock cycles equals summation I1 to n, and CPI's times instruction count I. Here we are. So we have a simple example. Given the instruction in the data below, we needed to calculate average CPI. Hello, we have different instruction types. For the first column, we have a load instruction, store instruction, arithmetic logic unit instruction, branch or jump instruction, and others. We have a different number of clock cycle for each type of instruction, and we have different percentage of instruction count. For example, instruction load type, it has 5 clock cycle, and it takes 20–50% of the instruction count. And for the store instruction, it takes 5 cycles, and it counts 15% of the instruction count. So I want you tell me average CPI. You also have 2 minutes to complete this. 2 minutes or 1 minute, because it's not difficult. Try to be fast. What is the average CPI? Huh? What is the average CPI for in different instruction classes? What is the average CPI? We have the formula here. We have different instruction types. We have the number of clock cycle for each instruction and the percentage count for instruction count. So I want you to tell me the average CPI. Huh? How much? How much is it? 4.75 cycles. You do take this average CPI. Equals the number of clock cycle for instruction load 5, and the percentage count for instruction count is 25%, plus the store instruction number of clock cycle is 5, and percentage of instruction count is 15, plus for arithmetic logic instruction of instruction, the instruction count is 40, and we have five clock cycle plus the number of clock cycle for branches is 3, and the instruction count is 15. Plus the last one, others, we have number of cycles 6, and the instruction count is 5%, that is 0.05, and said is 4.75 cycles. All right, now we have Amada's law, which help us to understand the maximum improvement in performance, and only when a part of the system is enhanced. We have Amada's law. The speed up is equals execution time for the older system, and divided by the execution time for the new system is equals 1 divided by 1 minus f. That is the fraction enhanced plus fraction enhanced divided by speed up enhanced. That is the factor by which the enhancement is lands fast. So here we have a simple example. A simple example, we suppose that we have a feature of a system used during execution of fraction of time f before improvement, and the speed up of the feature after enhancement is SUF. Then the overall speed up is overall speed up is 1 minus f plus f divided by SUF. So this is Amada's law. 1 minus f is the fraction of the task that can only run in serial. F is the fraction of the task that can run in serial. Now, this is an example. For example, if 90% of a program can be parallelized, that is f equals 0.95, and the parallel portion runs 20 times faster. The speed up equals to 20. So the maximum theoretical speed up would be less than 20 times because we have the serial portion of the program that still takes time to execute. So means that we have the speed up. The speed up equals to 1 divided by 1 minus f plus f divided by n. So let's fill in the value. We have 1 divided 1 minus 0.95. 1 minus 0.95, this is the portion of the task that can only run in serial. Then we have f which is 0.95. 0.95 divided by 20. Then you found what? This is the maximum time, the overall speed up of the system, because we still have 1 minus f, 1 minus 0.95, which can only run in parallel. So in today's class, we talked about classes of computers, starting from our PMD, personal mobile devices. We talked about desktop, servers, clusters, IoT. Then we have talked about the critical system issues linked with each class of computers. After that, we learned about parallelism architectures, single instruction, single data, single instruction, multiple data, multiple instruction, single data, or multiple instruction, multiple data. Then we have explored each parallel architecture. We also found out different user cases for each computer parallelism architecture. We talked about different concepts that can be used to assess computer performance. So I would like to know if there is any question related to today's class. Questions? So we are going to do a quiz for 10 minutes. Those who are sitting backside, please take the seat in front. Otherwise, you won't get papers. Those sitting the last 2 rows, please take the seat in front. Write down your student number and your English name and quiz number 2. Those sitting backside, 2 rows, you need to take the seat in front here. Otherwise, you won't get the paper. Mimbalama, take the seat in front. Please, the 2 rows, take the seat in front. Only use this paper, okay? Come. Write down your names, student ID, quiz number 2. You can give to your friends. Quiz number 2. Everybody has got a paper, right? Everybody has got paper? Yes or no? If you haven't got a paper, raise your hand. If you haven't got paper, please come here. You have to exercise. I will get done. Okay, that's it for today's class. See you next time.